Hi, this will be chapter 5, starting with chapter 5.1. A rigid sealed vessel contains a mixture of three different gases kept under the same conditions of temperature and pressure. The volume occupied by each gas is equal to the total volume of the vessel. See, when it's a closed vessel, and no matter how many gases you have inside, they do not care about the other gases. They're going to take all of the space they can. They do not care about anyone else. They're going to take the whole vessel. So that's how you can remember it. That they don't care about anyone. They're going to take the whole volume of the vessel for themselves. For question 2, determine the number of moles in a molar volume of gas. Here they said in a molar volume of gas. In a molar volume means in 1 mole. So without doing any math or without anything, you just put 1.0 moles and 1.0 mole. They want two significant figures. Whenever they tell you molar volume, they want it 1 mole. So yeah, here. The volume of oxygen in the gaseous state at STP is larger than in the liquid state. So any gas, the volume of its gaseous state is way larger than its liquid state or any condensed state. When most of the time, even when you're doing calculations and they tell you the volume in condensed phases like solids or liquids, you just say it's negligible. So the volume of the volume of any gas in the gaseous state is way larger than the liquid state. Here 4.00 decimeter cubed of a gas at STP has a mass of 20 grams. What is the mass of 1 mole of this gas? First you want the mass per decimeter cubed. So you do the mass divided by volume. You get 5 grams per decimeter cubed, and this is the molar volume. So you multiply that to cancel the units. Times 22.4 decimeter cubed over 1. The units cancel, as you can see, and you get 5 times 22.4 is 112 grams. 3 significant figures to the correct amount of significant figures, and that is section 5.1. Now 5.2. What is the kinetic theory of gas state? Gas particles collide with the walls of their containers to exert pressure. Yeah, that's the only thing from the options that's correct. Molecules of gas move faster at lower temperature. No, because its kinetic energy is directly proportional to absolute temperature, not inversely proportional. So when the temperature increases, the molecules will move faster. The average molecular kinetic energy is inversely proportional to the absolute energy. We just said that it's the opposite. Increasing the temperature of a sample of gas will cause the pressure to increase, not decrease. When gases are at the same temperature, the molecules of the gases have different average. No, they have the same. Sorry, when the gases are at the same temperature, the molecules of gases will have the same average kinetic energy. Why does the pressure of a gas sample increase when the temperature increases? I said before that when the temperature increases, the kinetic energy increases, making the molecules move faster and stronger, so they will hit the walls of the container more frequently and with more force. So the speed of the gas molecules increase. The gas molecules hit the container with wall more frequently. The gas molecules will hit the container walls more strongly. The number of gas molecules increase. No, temperature doesn't multiply them, it just increases their speed. And the mass of the gas molecules increase. You cannot change mass. Which of the following are true? The temperature of minus 273.15 degrees Celsius is 0 Kelvin. Yeah, we know that minus 273 is 0 Kelvin. But in the book itself, it wrote 0.15. You don't need to know that 0.15. You just use minus 2. minus 273, but they put it here for some reason. You just need to know that one Kelvin is 273 degrees Celsius. The size of a Kelvin degree is the same as the size of 1 Celsius. So 1K equals 1 degree Celsius. Here what they mean by size is not the actual thing, but on a thermometer you'll find that 1, for example here, 1 degree Celsius is 273 Kelvin, and 2 directly towards it 546 degrees Kelvin. So they have the same magnitude. Yeah. The volume of a fixed quantity of gas is inversely proportional. No, the volume is directly proportional to the absolute temperature. 0 Kelvin is the temperature not at which water freezes. No, 0 Kelvin is the temperature at which the volume of an ideal gas becomes 0. Yeah, when volume becomes 0. Five gases labeled A, B, C, D, and E have the same volume. They are placed under the same temperature. The molar gases are given in the table below. Circle the letter that has the high speed and underline that has the lowest speed. Now we know that the lighter gas is, the faster it will move. So the lightest gas here is A with the molar mass 4. So A is the lightest, and the heaviest one here is 71, or gas C. So you underline C. The molar gases of two gases A and B are 4 grams per mole and 32 grams per mole respectively. Choose the correct answer to complete the following sentence. At 25 degrees, the average kinetic energy. Okay, when at the same temperature, kinetic energy is the same for all masses at the same temperature. So at 25 degrees, the average kinetic energy of A is equal to the average kinetic energy of B. So at the same temperature, the average kinetic energy is equal to the other average kinetic energy. The temperature of a gas sample is increased from 0 to 75 degrees Celsius at a constant pressure. Drag and drop the picture that illustrates the change of volume. So here we have this picture with this volume, and then we added energy, so the particles moved faster and they exerted extra pressure on the walls, and at the same time volume is directly proportional to the absolute temperature. So as and the absolute temperature itself is directly proportional to the pressure, so volume is directly proportional to the pressure. So when the temperature increases, volume increases and pressure decreases. So when the temperature increased here, the pressure increased, causing the volume command to increase. The pressure of gas A is sealed in a container 0.5 atm. So here the partial pressure of gas A is 0.5. The addition of inert gas B to the container increases the pressure of the mixture to 0.75. So now the total pressure is 0.75. So they want the partial pressure of gas B, so 0.75 minus 0.5 equals 0.25 atm. And that's your partial pressure of gas B. Now for the question 8, the two inert gases A and B are mixed together. Information about the gases is given in the table below. The partial pressure is 0.5 and 0.6. They want the total pressure. Total pressure is you add all of the partial pressures. The total pressure Tp equals 0.5 plus 0.6, and it equals 1.1 atm. The total pressure of a gaseous mixture is 7.5 atm. Calculate the mole fraction of gases to complete the following table. So now we have the mole fraction X equals to P gas over P total. They gave us that the P total is 1.5, and they gave us the partial pressures. And we said X mole fraction is equal to P gas over P total. So P gas is for the gas A 0.75 over P total 1.5. You put it in your calculator, 0.75 divided by 1.5, you get 0.5. They want two significant figures for 0.50. And then for gas B 0.3 over 1.5, you get 0.2, and C 0.45 over 1.5 equals 0.3. Again, two significant figures, so you add a 0 here and a 0 here, so 0.50, 0.20 and 0.30. And to make sure that your mole fraction is correct, when you add all of these, they should equal to 1. For 0.5 plus 0.2 plus 0.3, it all equals to 1. The total pressure of a gaseous mixture is 2.5 atm. Calculate the mole fractions and the partial pressure of the gases to complete the following table. So now they give us the total pressure and the mass. So we first find the volume, the moles. They gave us the mass. For helium 4.8 over 4. Now we know that moles is mass over molar mass. It equals 1.2, and 8 argon is 40. 8 divided by 40, 0.2, and neon 12. 12 divided by 20 equals 0.6. And now if you want we want the total moles, so we add them all together. 1.2 plus 0.2 plus 0.6 equals to 2. So we have our N total is 2. And to find the mole fraction using moles, we have X equals N gas over N total. So starting with helium, N gas is 1.2 over 2, 0.6, and we want two significant figures for 0.60, and then for argon 0.2 over 2 equals 0.1. Again, two significant figures for 0.10, and neon 0.6 over 2 equals 0.30 for two significant figures. And then we want partial pressure. Partial pressure, we said before that P equals X times P total. So X for helium is 0.6 times P total 2.5, 0.6 times 2.5, 1.5, two significant figures. For argon 0.25 times 2.5, sorry, 0.10 times 2.5, mole fraction 0.10 times 2.5 is 0.25, two significant figures. And then for neon 0.3 times 2.5 equals 0.75, and two significant figures. So this is how you get this question. Here they want temperature in Celsius if they give it to us in Kelvin, and temperature in Celsius if they give it to us in Kelvin. So when you want to convert to Kelvin, you add 273, and if you want from Kelvin to Celsius, you subtract 273. So they gave us the first one, temperature in Kelvin, 725 minus 273 minus 273 equals 452, and that is your temperature in degrees Celsius. And then they gave us minus 68 plus 273, you get 205. 294 minus 273, you get 21. 273 plus 273, you get 546. You just convert عامة يعني add or subtract 273. 0.2 mole of oxygen gas and 0.6 moles of nitrogen gas are placed in an empty container. The total number of moles, you add all of the moles for 0.6 plus 0.2 equals 0.8. The mole fraction of nitrogen, you get the moles of nitrogen, 0.6 over 0.8, you get 0.75. Let's check on the calculator. You get 3 over 4 or 0.75. And the partial pressure of oxygen is, you can find the mole fraction using the same way you did for nitrogen, or you can do 1 minus mole fraction of nitrogen to get mole fraction of oxygen, and then you do partial pressure equals P total times X, the mole fraction. So P total is 2 times 0.25, you get 0.5. The volume of nitrogen in the container, we said that the gas takes the whole volume, so the volume is 12, and the volume of the container is 12, and the volume of nitrogen is 12. The fraction of the volume of the container occupied by oxygen is 100%. Oxygen occupies the volume 100% of the volume of the container, and so does nitrogen. For this question, a sample of air was found to be 7.20 grams of oxygen gas and 28.8 grams of nitrogen gas. Here they want the number of moles to begin with. We do the total number of moles, we do 7.2. We want number of moles, N equals M over M, and the total number of moles is just, you add all of the moles, 7.2 over oxygen gas. They said gas, and oxygen is diatomic in the gas, so 7.2 over 32 plus 28.8, also nitrogen gas, diatomic, over 28. You put it in your calculator, and you're supposed to get 1.25. Put it in the calculator, it's 1.25 and a lot of decimals after. You just round it up to 1.25. It's 1.253, you round it up into 1.25. The mole fraction of oxygen in the sample is, as we said before, mole fraction equals N over N total. So the N of oxygen is 7.2 over 7.2 over 32. It's 0.225 over 1.25. You get 0.180 for significant figures. The partial pressure of nitrogen, again, you can find the partial pressure of nitrogen using the same way you did for oxygen, but I like subtracting it. 1 minus 0.18 equals 0.82, and for partial pressure P equals X times P total. X here is 0.82 times 768 G. You get 623.2. But again, you rounded up a lot of stuff. I didn't round on my calculator, but it's 6.625. The percentage of oxygen by mass is, you find the total mass first, 7.2 plus 28.8. It's 36, your total mass. 7.2 over 36. You get 0.2. And you want it in a percentage, so you multiply by 100 and you get 20.0%. عشان significant figures. And this is 5.2. In 5.3, it's all about PV equals nRT. A certain mass of helium gas is placed in a cylinder fitted with piston at 25 degrees Celsius. While keeping the temperature constant, the piston is moved till the volume is decreased. You don't need to read all of this, except when they give you two variables, because then one of them is going to be in the thing. بس يعني عامة it's PV P1 V1 equals N1 R1 T1 capital T عشان they want the temperature in Kelvin. P2 V2 equals N2 R2 T2. N is constant, R is constant, we remove the R. So is N, certain mass of helium, you remove it. Also, temperature stayed constant here. So P1 V1 over P2 V2 equals 1. You can cross multiply, P1 V1 equals P2 V2. And P1 here is 120. And volume is 3. And in P2 they want P2. V2 is 2, so 2x. 120 times 3 over 2 equals x. You can cancel. 60 over 2, so 180 millimeter Hg. Now for question 2, I forgot to tell you, when you're doing two equations you can keep the pressure in millimeter Hg, but when you're doing it in one equation, only PV equals nRT, it has to be in ATM. So we have P1 V1 over P2 V2 equals nRT 1 over nRT 2. Or we can cancel, so can n. T1 is 25 plus 273. T2 is 125 plus 273. V stays the same, you can cancel it as well. P1 is 120, 25 plus 273, 298. 125 plus 273, 398. You can cross multiply. 120 times 398 equals 298p. So 120 times 398 over 298 equals P2. You can put it in your calculator. 120 times 398 over 298, you get 160 and a lot of decimals, 0.2 عامة يعني, so you can round it up to 160 equals P2. Which of the following are true about the particles of an ideal gas? They stop moving at 0 Kelvin, not Celsius. They are point masses, which means that they have the mass, but they don't have volume. So they have 0 volume. They have different average K. No, at the same temperature, they have the same average kinetic energy. They move in a straight line unless they undergo collisions. These are from the ideal gas law. You have to memorize that for the exam. What is the molar volume of an ideal gas at 32 degrees Celsius and 5 atm? So molar volume, so it's 1 mole. So PV equals nRT. N we can remove it because it's 1. P is 5. V is X until now. R is 0.082. And temperature, it is 32 plus 273. 0.082 times 305 equals 5x. You get 5x equals 25.01 and x is equal to 5. The 01 you can round it anyways, يعني, so it's not significant. So it's 5 decimeter cubed. What is the density of helium gas exerting a pressure of 760 millimeter Hg in a container at 27 degrees Celsius? So they want the density. There is the other equation, Pm equals dRT, R still being the M molar mass, P pressure, D density, R the ratio, and T temperature. They gave us the temperature, it's 27 degrees Celsius, which is 300 Kelvin, times 0.082 times X for density equals P is pressure, 760 millimeter Hg. To convert it into ATM, you divide by 760, so it's 1 ATM, and the molar mass is 4, so 4 equals 300 times 0.082 equals to 24.6x, and 4 divided by 24.6 equals x. 425 answer, and you get 0.16 and a lot of decimals, 0.162. So you round it up into two significant figures because of the choices. It's 0.16 grams per liter. What does the ideal gas law state? A gas is made of tiny particles with zero volume. When gas particles undergo collision, they obey the law of governing elastic collisions. Again, the ideal gas law, you have to memorize it. The molecules have the same amount of average kinetic energy at the same temperature. We said that many times in other quizzes as well. The pressure exerted by a gas is inversely proportional to its absolute temperature. No, we also said that pressure is directly proportional to the absolute temperature. And the gas particles collide in straight line. No, they move in straight line unless they undergo collisions. An evacuated cylinder fitted with a piston was filled with a certain mass of neon gas Ne at 32 degrees Celsius. Without changing the temperature, the piston was pulled to double the initial volume. So you have the same temperature. Mass never changes unless they tell you it changed. Either they added or removed. But here mass stays the same. The pressure, you have some mass of gas particles in a specific volume in a specific direction, causing said pressure. So when the volume is doubled, the gas particles have more space to move into, causing less collisions with the walls. So pressure decreases. By how much? Since the volume doubled, the pressure is going to half. half the initial, the pressure is half the initial, and the mass stays the same. An evacuated rigid container was filled with a certain mass of a gas X at 100 degrees Celsius. Without changing the amount of gas, the gas was heated to 300 degrees Celsius. Same as the last question, you have a container with gas particles in a specific volume. The volume doesn't change, only the temperature changes. So the temperature went from 100 to 300, so it increased, causing the kinetic energy to increase, causing command at the same time for the gas particles to collide with the walls and themselves more frequently and more powerfully. So the pressure will increase and the mass stays the same. A sample of 4 decimeter cubed of nitrogen gas is placed in a rigid container fitted with the piston at 100 degrees Celsius. While keeping pressure constant, the gas in the container was heated. Again, PV, P1V1 over P2V2 equals nRT1 over nRT2. N and R, they are constant, since they didn't say anything about the mass. Pressure is constant كمان. So 100, they want the temperature in Kelvin, of course. 100 plus 373, and 200 plus 273 is equal to 473. Volume 1 is 4, volume 2 we want to find it. So 4 times 473 over 373 equals V2. You can put it in your calculator. I just cross multiplied. 4 times 473 over 373. You get 5.072. They wanted 3 significant figures. If I round it up, it stays 5.07. A sample of 6 decimeter cubed of neon gas is placed in a rigid container fitted with a piston at 177 degrees Celsius. So here they changed the pressure and the temperature. N and R, they still cancel each other. For PV, P1V1 over P2V2 equals T1 over T2. T1 177 plus 273, 450, and 627 plus 273 equals 900. So you can cancel 1 over 2. P1 is 50, P2 is 100, V1 is 6, and V2 is X. 50 times 6 is 300 over 100x equals 1 over 2. You can cancel the 2 zeros, 3 over x. So x equals 6, cross multiply. Here is a question where they changed the mass for you. They said 12 more grams of methane gas are added. So we have the initial 12 and we add 12 more. So here volume stayed constant, we cross that out. Temperature stayed constant, and R is always constant. So P1 over P2 equals M1 over M2. So P1 is 1.2, P2 is X, M1 is 12, M2 is 24. 24 times 1.2 equals 12x. You move the 12 to the other side, over 12. So 24 times 1.2 over 12. You put it in the calculator, you get 2.4. 3 significant figures for 2.40. So for this question, a sample of 0.0440 grams of hydrogen gas H2 exerts pressure P at 57 degrees Celsius in a 3 liter rigid balloon. So we do PV, equals nRT. V is 3p equals n 0.0440 over 2. Hydrogen is 1, diatomic H2 times R 0.08. So we have times 0.08, and the temperature 57 plus 273 times 330. So 3p equals 0.022 times 0.08 times 330. You get 3p equals 0.5808. You divide it by 3, you get p equals 1936. 3 significant figures. If I round it, the 3 becomes 4 and the 6 is 0. So 194. Sorry, 0.194 ATM. A 25-liter sealed flask contains 3 different gases, He, Ar, and Ne. The gas mixture has a total pressure of 2.0 and ATM at 25 degrees Celsius. They want the partial pressure and the mass. So first we need to find the moles of each of them. We can find the moles with PV equals nRT. We do that for each of the gases. So PV, pressure is 2 and the volume is 25, so 50, equals N. We want to find that 0.080 for R times temperature. It's 25 plus 273, and you get 298. So 298 times 0.08, you get 50 equals 23.84 N. You divide 50 by the answer and you get the total mole is 2.1 equals N. So they gave you the mole fraction, they want the partial pressure. We can find the N of the gas by multiplying the mole fraction times N total, and we get the N gas. So for He, it's 0.5 times 2.1 equals, I'm doing times answer on my calculator if I'm not rounding. Now I am, equals 1.04, 1.05. Ar equals 0.25 times 2.1, and this is the same for same thing for neon, 0.25 times 2.1. So 0.25 times 2.1. For both of them it's 0.525. So now we have the individual. Now we want the partial pressure. Honestly, I just realized that we don't need to do all of this. If for the mass, yeah, but for the partial pressure we don't. So partial pressure is P total times times mole fraction. So for helium it's 0.5 times 2 equals 1. For argon, 0.25 times 2 equals 0.25 times 2 equals 0.5, and same thing for neon. Now for the mass, they're all gases, but most of them are diatomic. All of them are noble gases, but they're monoatomic. So you get all of the moles 1.05 divided by times mass equals nm. So 1.05 times for helium 4, so 1.05 times 4, you get 4.2. 0.5 times argon is 40 equals 20. Oh, sorry, 0.525 0.525 times 40 equals 21. 0.525 times 20 for neon equals 10.5. They want two significant figures, you round it up and it's 11. But that's how you do this. Don't forget significant figures. The number of moles of an ideal gas that occupies a volume of 1.46 and 10 to the power of 4 centimeter cubed at a pressure of 760 millimeter Hg and temperature 32 degrees is, so we use one equation, PV equals nRT, and 760 you divide by 760 again to get 80N. So pressure is 1, V, you have this in centimeter cubed, you want a decimeter cubed, so you divide by 1000 or 10 to the power 10 times 10 to the power of 3. The powers cancel, so it's 14.6. 14.6 equals nRT. We want the n. R is 0.082 here, it's given, and 32 degrees Celsius, 32 plus 273 equals 305 times 0.082. You get 14.6 equals 25.01 n, and then 14.6 divided by your answer, you get n is 0.583, and they wanted two significant figures, that's 0.58. Here they want the pressure, PV equals nRT. Pressure is they want the pressure 2 moles times 0.082 times temperature, here it's 17 plus 273 because they want it in Kelvin, 290 equals volume 2.4 x for pressure, so 2.4 equals x equals 2 times answer times 0.082. We get 47.56. You divided by 2.4 and you get x equals 19.81. They wanted three significant figures, if I round it up, 19.8. Here they want us to find a graph that is correct for ideal gases. We know that pressure is directly proportional to temperature, so it will be a straight line passing through the origin, just like this one. Here they want the graph that shows the correlation between pressure and volume. So we know that pressure is inversely proportional to volume. As long as volume increases, pressure is decreasing. So this one is the correct one. Here again, PV equals nRT. P is 1 ATM, so it's just V equals N 56 grams over the molar mass of N2, so 28, times R 0.082 times temperature 25 plus 273. You put that in your calculator. It's 56 over 28 times 0.082 times 25 plus 273. You get V is equal to 48.87. They want three significant figures. We round it up, 48.9. An ideal gas occupying the volume of 25 decimeter cubed under a pressure of 3 atm is heated from 27 to 177. If pressure is kept constant, so PV over PV equals nRT over nRT. You remove the n and the r. If pressure is kept constant, so V equals T, the volume will be 27 plus 273. You get 300 for T1, and 177 plus 273. You get 450 for the other one. V1 is 3 and x, so 450 times 3 over 300 equals x. Cancel the zeros. I divide by 15, 2 and 3, 9. Uh, 450 times 3 over 300. Here, an ideal gas occupying a volume of 25 decimeter cubed under a pressure of 3 atm is heated from 27 degrees Celsius to 177 degrees Celsius. So, pressure stays constant for part A, so pressure cancels, N cancels, R cancels. V1 over V2 equals T1 over T2. T1 is 27 plus 300, or plus 273 is 300, over 450 for T2 equals V1 is 25 over X, so 25 over 450 over 300 equals V2. You put it in your calculator, so 25 times 450 over 300, you get 37.5. Two significant figures, 38. That's for part A. For part B, they wanted if the pressure stayed constant, if the volume was kept constant, sorry. So it's P, volume cancels, N and R always cancel, almost always cancel. So P1 over P2 equals T1 over T2. P1 is 3, P2 is X, T1 is 300 over 450. You can cancel the 0 and it's 2 over 3. Cross multiply, 9 equals 2x. So 4.5 equals x, two significant figures, and it's correct. A 5 decimeter cubed flask is filled with dry air to 850 millimeter Hg pressure. Air is 20% O2 and 80% N2 by volume, which means mole ratio. So the volume of oxygen in the flask is the total volume of the flask itself, so it's 5 decimeter cubed. And the partial pressure, they gave you the mole fraction of nitrogen, it's 80%. So you multiply that 0.8 times 850. So 0.8 times 850, you get 680. And you can't really change this into two significant figures, here it is. So here they said consider a gas sample composed of 70% neon and 30% helium. And they want the average molar mass. So you do 70%, so 0.7, times neon, it's 20, and 30%, 0.3, times 4, plus between them, you get 0.7 times 20, 14 plus 0.3, 4, 14 plus 1.2, and you get 15.2. Now the density is, density is 15.2 over 22.4. So 22.4 because it's the molar volume. So 15.2 over 22.4, and you get 0.67857. And they want three significant figures. If I round it up, 5, so 0.679.